What if the strangest thing about quantum physics is not the physics? Everyone has heard the greatest hits: the cat that is alive and dead, the particle that goes through both openings at once, the thing that refuses to decide until somebody looks. Those are the stories. Here is the part that does not get told. Last year, somebody went and asked more than 1,100 physicists a very simple question. What do you think this theory is telling us about reality? 100 years after it was written. 100 years of it never once giving a wrong answer about anything. And the largest group of them, the winners, the plurality, came in at 36%. And when you looked inside that group, most of them did not even agree with each other about whether the central object in their own equations corresponds to anything real. Not a fringe dispute. The people who use it every day. So what is it that a century of extraordinarily careful people have circled and measured and written into theorems and still not quite said out loud? Get comfortable, subscribe if you haven't already, and stay with us, because by the end of tonight you will know exactly what that thing is and why almost nobody says it. Let's begin. Part 1. The question. Nobody answered. 100 years ago, a young man with hay fever went to an island in the North Sea because nothing grows there. His name was Werner Heisenberg and the island was Helgoland, a bare red rock about 30 miles off the German coast with no trees, no pollen and almost nothing to do. He had gone there to stop sneezing. What he actually did in the space of a few feverish days in the summer of 1925 was write down the first working version of quantum mechanics. He was 23 years old. He later described climbing a rock formation at dawn afterward and watching the sun come up, and he said he had the distinct feeling of looking through the surface of atomic phenomena at something strange and beautiful underneath, and of being almost dizzy at the thought that he now had to follow it. He never quite got to the bottom of it. Neither has anyone else. In July of 2025, on the 100th anniversary of that week on Helgoland, the journal Nature published the results of a survey. Now, journals run surveys all the time. They ask researchers about funding, about job prospects, about whether they are happy, about whether they think their field is in trouble. This one was different. This one asked physicists a question that sounds almost childish when you say it out loud. What do you think quantum mechanics is actually telling us about reality? More than 1,100 researchers answered, and the results are the reason you are listening to this. Here is the headline number. The largest single group of respondents, 36% of them, said they favoured the Copenhagen interpretation. That is the orthodox reading, the one associated with Niels Bohr and with Heisenberg himself, the one that gets taught in undergraduate courses as if it were simply what the theory says. 36%. That is the winner. That is the most popular answer. Sit with that for a second, because I think most people assume the number would be higher. Not 70%, not 80, 36. Which means that 64% of the physicists who answered this survey, nearly 2 out of every 3, do not hold the view that gets taught as the default. And they were not clustered in some tidy second camp either. They were scattered. Many worlds, in which every possible outcome actually happens somewhere. Pilot wave theory, in which particles always have definite positions and a real wave pushes them around. Relational quantum mechanics, in which there is no such thing as the state of a system, only the state of a system relative to another system. Cubism, in which the mathematics describes your personal beliefs rather than the world. Consistent histories, spontaneous collapse, and a substantial group who selected in effect none of the above. But that is not the number that stopped me. This is the number that stopped me. Among the respondents who chose Copenhagen, the winners, the plurality, the ones who all pick the same box, only 29% said they believe the wave function describes something real. Nearly 2/3 of them said it merely encodes information, or probabilities, and does not correspond to anything that exists out there in the world. Do you see what that means? The largest group of agreeing physicists in this survey was not actually agreeing. They had picked the same label off a menu while holding flatly incompatible views about whether the central mathematical object in the entire theory corresponds to anything real. It is a bit like polling a room full of people about their favourite animal, having 36% say dog, and then discovering that 2/3 of those people do not believe dogs exist. There was one more split in the data, and it is quietly revealing. Almost half of the experimental physicists who responded favoured Copenhagen. Among the theorists, it was 33%, The people who build the apparatus, who align the mirrors, who sit up at 3 a.m. watching a counter increment, those people are more comfortable with the reading that says do not ask. The people whose entire job is to ask are less comfortable with it. That is not a coincidence. That is a division of labour that has hardened into a division of belief. And before you assume this is some one-off result, a fluke of one survey in one anniversary year, I want to put 2 older data points next to it. In 2013, 3 physicists, Maximilian Schlosshauer, Johannes Koffler, and Anton Zeilinger, who would go on to win a Nobel Prize, handed out a questionnaire at a conference specifically about the foundations of quantum mechanics. 16 multiple-choice questions, 33 participants, all of them people who had travelled to a meeting dedicated to exactly this subject. They found no consensus. Not on the big questions, not on the small ones. On the essential points, the room did not agree with itself. In 2016, 2 researchers sent questionnaires to 1,234 physicists across 8 universities. 149 of them wrote back. Copenhagen took 39%, Many Worlds took 6%, Pilot Wave Theory took 2%, everything else combined took 17%, and 36%, more than a third of the respondents, reported having no preferred interpretation at all. Not that they were undecided between 2 options, that they did not have a position on what their own theory means. So that is where we are. 3 surveys, 12 years apart, and the picture does not move. A third of professional physicists have no opinion. A third of the ones with an opinion turn out to disagree with each other inside their own camp. And this has been the situation, more or less continuously, since the 1920s. Now, I want to be very careful here, because there is a version of this story that is dishonest, and I am not going to tell you that version. The dishonest version says quantum mechanics is broken, or unproven, or a house of cards. It is none of those things. Quantum mechanics is the most precisely tested description of nature that human beings have ever constructed. Quantum electrodynamics predicts the magnetic behavior of the electron to roughly 12 significant figures, and when you go and measure the electron, it agrees. 12 significant figures. That is the equivalent of predicting the distance from here to the moon and being wrong by less than the width of a human hair. And it is not just precision, it is ubiquity. The device you are listening to this on contains billions of transistors, and every one of them works because electrons behave in the way this theory says they behave. Lasers, LEDs, magnetic resonance imaging, the atomic clocks in the satellites overhead that let your phone know where you are. All of it runs on quantum mechanics performing exactly as advertised. The theory has never once been caught giving a wrong answer to a question of the form. If I build this apparatus and run it 1,000 times, what will I see and how often? That question, it answers perfectly, flawlessly, for 100 years. Economists have estimated that something like a third of the gross domestic product of the industrialized world depends on technologies that could not exist without it. This is not a fringe theory waiting for confirmation. It is load-bearing, and there is a small, almost embarrassing detail about how the probability part of it arrived. In 1926, Max Born was writing a paper about particles scattering off each other, and he added the rule that connects the mathematics to the odds of what you will actually see. He added it in a footnote, in proof, after the paper was already written. The single sentence that tells you how to get a prediction out of quantum mechanics, the sentence that every experiment in the last century has confirmed, was an afterthought scribbled into the margins of something else. There is a different question it has never answered. And the different question is this: what is happening when nobody is measuring? That is the whole video. That is the entire thing. Everything from here on is an unpacking of why that question is harder than it sounds, why every attempt to answer it has cost somebody something they did not want to give up, and what has happened over the last 8 years that has made the situation considerably worse than the textbooks admit. Because there is a phrase for how the field has handled this. A physicist named David Mermin coined it, though he later noted with some amusement that people kept attributing it to Richard Feynman instead. The phrase is, "shut up and calculate." It is a joke. It is also, for about 80 years, the closest thing this field has had to an official policy. And in 2025, somebody finally went around and counted what happens to a discipline when 1,100 of its practitioners follow that policy for a century without ever comparing notes. Before we get to what they found underneath, though, I need to show you the thing they were arguing about. Because the strangeness at the heart of this is not complicated. It is not the sort of thing you need a degree to feel. It fits quite comfortably inside a box. Part 2. The box that does not decide. Imagine somebody hands you a box. It is a small box, closed, unremarkable, the kind of thing you could hold in one hand, and you are told that this box will give you whatever you ask it for. You ask for an apple, you open it, there is an apple. You ask for a pencil, you open it, there is a pencil. You ask for something ridiculous, a unicorn, say, and you open the box and there it is, small and improbable and entirely present. That is a nice trick, but it is not the strange part. The strange part is this. The box does not decide what is inside it until you open it. Now, I want to slow down here, because almost everybody's brain does the same thing at this point, and the thing it does is wrong. Your brain hears, the box has not decided, and quietly translates it into the box has decided and you have not been told. Those are not the same statement. They are not even close. One is a fact about your information. The other is a fact about the box. If the box has already decided and is simply keeping it from you, then there is an answer, sitting there, waiting. The apple is in the box or it is not. Your ignorance is a curtain, and behind the curtain is a stage with one object on it. That is not what quantum mechanics says. Quantum mechanics says there is no object behind the curtain. Not a hidden one, not a small one, not one you would find if you were clever enough. Before you open it, there is no fact of the matter about which thing is inside. And the theory does not say this because it is being coy. It says it because if there were a hidden answer sitting there the whole time, the experiments would come out differently, and they do not. Let me put you inside that for a moment. You are holding the box. It weighs almost nothing. There is no rattle when you shake it, no shifting weight, no clue at all, and what is inside it right now is not an apple, and not a pencil, and not a unicorn, and not nothing. It is all of them, in a sense that the English language was not built to carry, layered over one another without any one of them being the one that is really there. There is no photograph you could take through the lid that would show you the truth because there is no truth of that kind in there yet. And then you open it, and there is an apple, one apple. Solid, ordinary, sitting in the bottom of the box like it has been there the whole time. And here is the part that should bother you, the part I want you to carry for the next 2 hours. There is now no record anywhere in the universe of the pencil, not a trace, not a faint impression, not a residue. The alternative that was, a moment ago, exactly as present as the apple, is gone so completely that nothing in the box, nothing in the room, nothing in the light that fell on it, retains any evidence that it was ever a possibility at all. The box has not decided yet. That is the sentence. Remember it. We are going to come back to it later, and when we do, there is going to be somebody inside. Now, you are entitled to ask a reasonable question, which is, how could anybody possibly know that? If the answer is hidden until you look, and looking produces an answer, how do you tell the difference between a box that was undecided and a box that was merely secretive? The answer is that you do not open the box. You count. Here is what I mean. Send something small, an electron, a photon, a molecule, toward a barrier with 2 openings in it, and let it land on a screen behind. Do it once, you get 1 dot. Do it again, another dot. Do it 100,000 times and a pattern accumulates on that screen, and the shape of the pattern tells you what was happening on the way through. If each one genuinely went through one opening or the other, like a very small tennis ball, the pattern is simple. It is the pattern you would get from the left opening alone, added to the pattern you would get from the right opening alone. 2 soft heaps. That is what it took one path looks like. That is not what you get. What you get is a set of stripes. Bright band, dark band, bright band, dark band, marching out across the screen. And crucially, there are places on that screen that are dark when both openings are available and bright when you close one of them. Which is to say, opening a second route to a place made it harder to arrive there. That is not a thing a tennis ball can do. That is a thing waves do, when a crest from one route meets a trough from the other, and they cancel. Those stripes are called interference fringes, and they are the fingerprint. They are the actual physical, measurable evidence that the thing did not take one path, and they are not a rare or delicate result. This experiment has been done with electrons, with neutrons, with whole atoms, with molecules containing thousands of atoms. The stripes show up every time, and now the detail that turns this from a curiosity into a problem. If you put any device anywhere along the route that records which opening the thing went through, any device at all, it does not have to be a person, It does not have to be conscious. It can be a single stray photon that bounced off at the wrong moment. The stripes vanish. Instantly. Completely. You get the two soft heaps. The moment which path information exists anywhere in the world, the box has decided. There is one more thing worth saying about those stripes before we move on, because it is the detail that makes the whole subject impossible to wave away. The fringes are not a qualitative smudge. They have positions, and the positions are predictable to extraordinary accuracy from the mass of the thing you sent through and the geometry of the apparatus. You can calculate in advance where the dark bands will fall, build the machine, run it, and find them exactly where the arithmetic put them. The theory does not merely say something odd happens on the way through. It says precisely how odd, in units, to as many decimal places as your instrument can resolve. That is why nobody in the field treats superposition as an interpretive flourish. It is a measurement with error bars, so the theory needs two rules, and this is where the trouble starts. The first rule is the Schrödinger equation, and it is beautiful. It is smooth. It is deterministic. Feed it a state now, it tells you the state later with total certainty. It is reversible, meaning you can run it backward and recover exactly where you started. And it is linear, which is the technical word for the property that causes all the strangeness. If one thing can happen, and another thing can happen, then the sum of them can also happen. Under the first rule, superpositions are not some exotic special case. They are what you get automatically, forever, unless something intervenes. The second rule says that when you measure, you get one outcome, not a sum, not a blend, one. And the odds of each possible outcome are given by the size of its share in the superposition, squared. This is that footnote of Born's, and it is the rule that makes the theory usable. The two rules do not fit together. The first one is continuous, the second is a jump. The first is reversible, the second destroys information about everything that did not happen. The first says superpositions persist, the second says they do not. And here is the thing. Nowhere in the theory is there an equation that tells you when to stop using the first rule and start using the second. There is no mass at which it switches over, no size, no temperature, no number of atoms, no definition of what counts as a measurement, or what counts as an observer, or what counts as looking. The standard textbook presentation of the most successful theory in the history of science is two incompatible descriptions of change, stapled together, with a note in the margin that says, use the first one until something happens, then use the second one. That gap has a name. It is called the measurement problem. It has been sitting in exactly that spot, unfilled, since the 1920s, and the first person to point at it and say out loud that this was absurd was not some outsider or critic. It was one of the men who wrote the equation. He made his point by putting a cat in a box. Part 3. The cat was an insult. In 1935, Erwin Schrödinger sat down to write what has become the most famous thought experiment in the history of physics, and he did it because he was annoyed. This is the part that gets lost. The cat is not a teaching aid. It was never meant to help anybody understand quantum mechanics. It was a complaint. Schrödinger had written the wave equation that sits at the heart of the theory. His name is on it. It is the first of those two rules I just described, and he had spent the better part of a decade watching his colleagues in Copenhagen build an interpretive framework around it that he considered evasive. So he constructed the most absurd consequence he could think of, wrote it up and published it, essentially as a challenge. If you believe what you say you believe, he was saying, then you have to believe this too. And look at it. Look at what you have to believe. Here is the setup, and it is worth walking through carefully because the details are the argument. You take a steel chamber. Inside it you place a cat. Alongside the cat you place a tiny amount of radioactive material. And Schrödinger is specific about this. He says a quantity so small that over the course of an hour perhaps one atom decays and perhaps none does. Radioactive decay is genuinely, irreducibly quantum. There is no mechanism inside the nucleus keeping a schedule. The atom does not know when it is going to decay, because there is nothing in it that knows. Now you wire that atom to a Geiger counter. If the atom decays, the counter clicks. The click releases a hammer. The hammer shatters a small flask of hydrocyanic acid, and the cat dies. Everything in that chain is ordinary. Counters, hammers, glass, poison. There is nothing quantum about a hammer. But the whole apparatus exists for exactly one purpose, which is to take a single undecided atom and amplify its undecidedness up through a chain of ordinary objects until it reaches something the size of an animal. After 1 hour, the theory says the atom is in a superposition of decayed and not decayed. Fine. Nobody in 1935 would have argued with that, but the counter is wired to the atom, so the counter is now in a superposition of clicked and not clicked. The hammer is in a superposition of fallen and not fallen. The flask is intact and shattered, and the cat, following the mathematics honestly, taking the first rule at its word, applying it to everything as the equation says you should, the cat is alive and dead. Schrödinger's actual phrase for the resulting picture was that it was a ridiculous case. He said the state would express the living and dead cat mixed or smeared out in equal parts, and he clearly expected his readers to recoil. They did not recoil. They adopted it. The cat became the mascot of the very position it was written to embarrass, which is one of the more remarkable things that has ever happened to a piece of scientific rhetoric. And here is what makes the argument so hard to escape. You cannot get rid of the cat by saying the apparatus is too big or too warm or too complicated for quantum mechanics to apply to it, because the whole point of the apparatus is that every single link in the chain is a perfectly normal physical interaction. If quantum mechanics applies to the atom, and the counter physically interacts with the atom, and the hammer physically interacts with the counter, then either the theory applies all the way up, or it stops somewhere. And if it stops somewhere, you have to say where and why, and what physical process does the stopping. Nobody has ever been able to say. That is the entire problem in one sentence, and I want you to notice where you are standing in that chain, because this is not an abstraction about cats. Every measurement any human being has ever made works the same way. Something small and undecided interacts with something slightly larger, which interacts with something larger still, until eventually a needle moves, or a number appears on a screen, or a photon lands on your retina, and a chain of ordinary chemistry carries it inward. You are the far end of an amplifier. Whatever process is supposed to turn a superposition into a single fact, it happens somewhere between the atom and you, and the theory that describes both ends of that chain in exquisite detail has nothing whatsoever to say about the middle. There is a second thing in that 1935 paper, and it is arguably more important than the cat, though far fewer people know about it. In the same essay, Schrödinger coined a word. In German it was Verschränkung. In English we call it entanglement. And he described it not as a curiosity, but as, in his words, the characteristic trait of quantum mechanics, the one that enforces its entire departure from classical lines of thought. Entanglement is what happens when two systems interact and afterward can no longer be described separately. Not because we lack information about them, but because there is no separate description. The pair has properties that neither member has on its own. Measure one, and you instantly know something about the other, no matter how far apart they have travelled since. And in that same year, 1935, Albert Einstein and two colleagues, Boris Podolsky and Nathan Rosen, published a paper that used exactly this feature as a weapon. Their argument, stripped down, was this. If measuring one particle here tells you something definite about a particle over there, and nothing you did could have reached across the gap in time, then the thing you learned must have been true over there all along. The theory does not include it. Therefore the theory is incomplete. There must be more to the story, some extra layer of detail the mathematics is not capturing. I want to be precise about Einstein's objection, because it gets caricatured constantly. He's remembered for the line about God not playing dice, and that line has been sanded down into a complaint about randomness, as though he simply could not stomach probability. That is not what was bothering him. Einstein had spent his career building descriptions of things that are there whether or not you're looking at them. Fields, curvature, geometry. What he could not accept was a theory whose fundamental objects only become definite when somebody checks, because a theory like that is not describing the world. It is describing our encounters with the world, which is a smaller and less interesting job, Bohr replied. His reply is famously difficult to pass, and physicists have argued for 90 years about exactly what it says, which tells you something in itself. The gist was that the question Einstein was asking, what is the particle really doing, was not a legitimate question, because the properties in question do not exist independently of the whole experimental arrangement used to observe them. That was the argument. It ran through the 1920s and 30s, most famously at the Solvay conferences in Brussels, where the density of talent in the room was almost comical. 17 of the 29 people who attended the 1927 meeting either had or would go on to win a Nobel Prize. Einstein would arrive at breakfast with a new thought experiment designed to break the theory. Bohr would spend the day taking it apart. By dinner it was usually resolved and Einstein would start again the next morning. And then the argument stopped. Not because it was settled, because the theory started working so well that arguing about it began to look like a waste of a career. Quantum mechanics went to work, on chemistry, on solid-state physics, on the bomb, on the transistor, and the interpretive question got filed under philosophy, which in a physics department is roughly where you file things you would like people to stop bringing up. Schrödinger himself never made peace with it. Late in life he said of quantum theory that he did not like it, and that he was sorry he had ever had anything to do with it. A remarkable thing to say about a field you helped invent and won a Nobel Prize for. The cat stayed, detached from its purpose, printed on t-shirts, deployed in 1,000 lazy metaphors about ambiguity. And the question it was built to ask, where exactly does the first rule stop and the second one start, sat there unanswered for another 80 years, while the chain of ordinary objects between the atom and the cat got quietly longer and better understood. Because to see why that chain is such a problem, you have to look at what is actually at the bottom of it. And the bottom is stranger than a decaying atom. The bottom is not made of things at all. Part 4. Fuzziness is not ignorance. There is a very old human instinct that says if you keep cutting something in half, eventually you will reach the piece that cannot be cut, and that piece will be the thing everything is made of. The ancient Greeks thought the answer might be air or fire or water or earth, which sounds naive now, but was a genuinely radical proposal at the time, because it said the enormous variety of the world could be built out of a short list. That instinct, that there is a short list, has been right every single time. What has been wrong every single time is what is on it. A century ago the answer was the atom, and the word itself means uncuttable. Then people cut it. Inside there was a nucleus and a cloud of electrons. Then they cut the nucleus, and inside there were protons and neutrons. Then they cut those, and inside there were quarks. Now atoms are still extraordinary objects, and it is worth pausing on them, because almost everything you have ever touched is a statement about atoms. There are roughly 90 elements that occur naturally on Earth, every one of them assembled by processes in stars or in the collisions of dead stars. Each has a personality, hardness, colour, melting point, boiling point, density, how well it conducts, how greedily it grabs electrons. And here is the remarkable thing. All of that personality, every chemical property an element has, is determined by one number. Not 2. 1. The number of protons in the nucleus. Change it by 1, and you have a different element with an entirely different life. Everything else follows. An atom is also, in its own right, a fully quantum object with its own energy levels and its own conservation laws, and it interacts with all 4 of the known fundamental forces. In a real sense, you can see the whole of physics inside a single atom if you look closely enough. But the cutting does not stop at quarks, and this is where the ground gives way. Because the deepest layer of the modern description is not made of small things at all. It is made of fields. A field in this sense is a quantity that has a value at every point in space, everywhere, always, whether or not anything interesting is happening. And what we call a particle is not an object sitting in a field. It is an excitation of the field, a hump in it, a localized packet of energy, the way a wave is not an object in the ocean but a shape the ocean is temporarily making. A photon is an excitation of the electromagnetic field. An electron is an excitation of the electron field, which is a genuinely strange sentence the first time you meet it, because it means that every electron in your body is a ripple in something that also exists, quietly, in the vacuum between galaxies. And because those fields are always there, the vacuum is not empty. It cannot be. A field that is exactly zero everywhere with exactly zero uncertainty is forbidden by the same rules that forbid a particle from having a precise position and a precise momentum at the same time. So even in the emptiest region of space you can imagine, the fields hum. Virtual particles flicker into existence and vanish again, borrowing energy that is not there and paying it back before anyone can check. Those flickers are not a metaphor. They shift the energy levels of atoms by amounts we can measure. In 1947, Willis Lamb found that 2 energy levels in hydrogen that the existing theory said should be identical are in fact very slightly different, and the size of that difference is exactly what you get if you assume the electron is being continuously jostled by the empty space around it. Nothing was in the room. The nothing had a measurable effect. So why do we spend all our time talking about particles if fields are the deeper thing? Because the field cannot be observed directly. Any observation requires an exchange of energy, and an exchange of energy forces the field to hand you a quantum, a particle. The particle is what a detector can register. The field is what the mathematics requires. The thing we can see is downstream of the thing that exists, and that gap is going to matter enormously later on. It is worth dwelling on spin for a second, because it is the one item on that list with no honest picture attached to it. The name is a historical accident. Spin behaves mathematically like rotation. It carries angular momentum. It responds to magnetic fields the way a spinning charge would. But an electron is not a small ball turning on an axis, and if you insist on modelling it that way, you can show in about 2 lines that the surface would have to be moving faster than light. Spin is a property with no classical relative. It is one of the 3 numbers that define what an electron is, and there is no image of it that survives contact with the mathematics. Physics is full of these, quantities that are unquestionably real, that you can measure to a dozen decimal places and that refuse to be a picture. Now, here is what I find genuinely startling about all this. Given how strange the underlying picture is, you would expect the definition of a particle to be complicated. It is not. It is almost insultingly short. Mass, electric charge, intrinsic angular momentum, which we call spin. That is essentially the whole specification, and every electron in the universe has identical values for all 3. Not similar, identical. There is no such thing as a slightly heavier electron, or a scuffed one, or an older one. This is why electrons are interchangeable in a way that no object in your kitchen is. Swap 2 of them, and nothing has physically changed. And that fact, that deep sameness, is the reason the periodic table has the shape it has, and the reason matter does not simply collapse into itself. Almost every particle also has a partner with the same mass and the opposite charge, an antiparticle. Antimatter is real, it is made routinely in collisions, and it is essentially absent from the visible universe. Everything we can see is matter. Nobody knows why. That is one of the honest open wounds in physics, and I mention it here mostly to make a point about intellectual honesty. The field is entirely capable of saying we do not know when the not knowing is about a fact. It gets much more uncomfortable when the not knowing is about what the theory means. Which brings us to uncertainty, and to the most misunderstood idea in the whole subject. Werner Heisenberg's uncertainty principle says that the more precisely you pin down a particle's position, the more its momentum blurs, and the other way around. And almost everyone is first taught this with a story about disturbance. You have to bounce something off the particle to see it, and the bouncing knocks it around, so you cannot know both. That story is wrong. Or rather, it is a true thing that is not the reason. The reason is structural. It is not that the particle has a definite position and a definite momentum, and our clumsiness prevents us from reading both. It is that a thing with a perfectly definite position is, mathematically, a thing built out of every possible momentum at once, and a thing with a perfectly definite momentum is spread out over all of space. They are not 2 properties competing for measurement time. They are 2 descriptions of the same object, and the sharper one gets, the more the other necessarily smears. The fuzziness is not in the instrument, it is in the thing, and notice what that does to the box. We started this part looking for the layer of reality that finally decides. What we have found instead is that the deeper you cut, the less there is down there that could possibly do any deciding. There is no tiny mechanism at the bottom keeping track of which outcome it will produce. There is a field, and a hump in it, and 3 numbers, and a set of odds. Which raises an obvious question. How would you ever prove that? How do you demonstrate that the universe is not simply keeping a secret? Somebody worked out how, and it required light that left its source before the Earth existed. Part 5. The experiment built to kill a comfortable idea. For about 30 years after Einstein died, there was a comfortable answer available, and a lot of sensible people quietly believed it. The comfortable answer goes like this. The randomness is not real, it is bookkeeping. When 2 particles are created together and fly apart, they leave with instructions, some deeper set of properties the theory does not track, fixed at the moment of creation, carried along like sealed envelopes. When you open your envelope and find a result, it was in there all along. The correlations between distant particles are not spooky at all. They are the same reason two people who split a pair of gloves at the airport will find, on landing, that one has the left and one has the right. Nothing travelled, nothing decided. Everything was determined at the start and you simply did not have the information. This is called a local hidden variable theory, and it is a genuinely reasonable position. It restores everything Einstein wanted. The world is made of things with properties. Measurements reveal, they do not create. Nothing influences anything faster than light. It is the intuition every human being is born with, written out carefully in physics. In 1964, a physicist named John Stuart Bell killed it, and he did it in a way that is still, 60 years later, one of the most beautiful pieces of reasoning anyone has produced. Bell did not argue about philosophy. He asked an arithmetic question. Suppose the comfortable answer is true. Suppose the particles do carry instructions. Then when you measure them along various different angles and compare the results, there is a limit, a hard ceiling, on how strongly the results can agree. Not a suggestion, a number. Any theory of that type, no matter how baroque, no matter what the instructions say, cannot push the correlation past a certain value. Quantum mechanics predicts that you can push past it. That is what makes Bell's work so extraordinary. He took a question that had been treated as a matter of temperament for 3 decades and converted it into something you could settle with a machine. In the standard version of the test, the classical ceiling is 2. Quantum mechanics allows you to reach about 2.828, a number known as the Cyrilson bound. And here is a small strangeness that almost never gets mentioned. The mathematics of pure logic would permit you to go all the way up to 4. The universe goes past the classical limit but stops well short of the logically available maximum, and to this day nobody fully knows why it stops where it does. So people went and measured. The first attempts were in the 1970s, and they were done, in some cases, by people who fully expected the comfortable answer to win. John Clauser has said publicly that he thought he would confirm local realism, and that his early experiments were regarded by senior colleagues as a poor use of resources. He got the opposite result. Then Alain Aspect, in France, refined the setup so that the measurement settings were changed after the particles were already in flight, which closed off the possibility that the detectors had somehow agreed in advance. But every experiment leaves a crack, and the cracks in Bell tests have names. Maybe the detectors only caught a biased sample of the particles. Maybe a signal travelled between the two sides. Closing all of the cracks at once in a single experiment took 50 years. It happened in 2015, in Delft, in the Netherlands. Picture it. It is the middle of the night on a university campus. In 2 separate buildings, 1,280 metres apart, call it 3/4 of a mile, there are 2 diamonds. Each has a deliberate flaw in it, a place where a nitrogen atom sits where a carbon atom should be, and that flaw traps a single electron whose spin can be prepared, entangled with a partner, and read out. The 2 sites are far enough apart that light cannot cross between them in the time it takes to choose a setting and record a result. That distance is not an aesthetic choice. It is the whole point. It is what makes it physically impossible for one side to know what the other side did. The experiment ran for 220 hours, 9 days of continuous operation, and in 9 days it produced 245 valid trials. Do the arithmetic. That is roughly 1 usable event per hour. For 9 days, somewhere in that building, a machine sat in the dark and about once an hour successfully entangled 2 electrons 3/4 of a mile apart and asked them a question. Everything else was failure. Photons lost, timing missed, heralding signals that never arrived. 245 times it worked. The way they managed it is worth a sentence, because it is the trick that made the whole thing possible. They did not try to send an entangled pair from one building to the other and hope both halves survived the journey. Instead, each diamond emitted a photon that carried information about its own electron, and both photons were sent to a third station roughly midway between them, where they were made to interfere. Most of the time, nothing useful happened, but occasionally the detectors at that middle station fired in a very specific pattern that could only occur if the 2 distant electrons had become entangled with each other, and that pattern acted as a herald, an announcement that a valid pair now existed. Only the heralded runs counted. That is why the detection efficiency was high enough to close the sampling crack, and it is also why 9 days of running produced 245 events instead of 245 million. The number that came out was 2.42, the ceiling was 2. That result is the end of local hidden variables, not weakened, not challenged, ended. Whatever the world is doing, it is not carrying sealed envelopes. But there was one crack left, and it is the strangest of them all. It is called the freedom of choice loophole, and it says, what if the settings you chose were not free? What if the random number generator that picked the measurement angle was itself correlated, through some long causal chain, with the particles being measured? Then the conspiracy is not between the two detectors, it is between the past and everything. In 2018, a team including Anton Zeilinger dealt with that by handing the choice to the sky. They pointed telescopes at two quasars, the incandescent centers of distant galaxies, and used the color of the arriving light to set the measurement angles in real time. A photon of one color, one setting. A photon of another color, the other setting. The light from the first quasar left its source roughly 7.8 billion years ago. The light from the second left roughly 3.2 billion years ago. Think about what that means. For the freedom of choice loophole to save local realism, the correlation between those settings and the particles in a laboratory in Vienna today would have had to be arranged before the Earth existed, before the Sun existed, when the universe was less than half its present age. The result violated Bell's inequality by 9.3 standard deviations across more than 30,000 photon pairs, with a probability of arising by chance of about 7 times 10 to the minus 21. That is odds of roughly 1 in 100 quintillion. There is a related experiment, the Big Bell test, that took the opposite approach and recruited about 100,000 members of the public to generate the settings by playing an online game on the reasoning that if human choices are free, that ought to be good enough. Same answer. In 2022, the Nobel Prize in Physics went to Alan Aspect, John Clauser, and Anton Zeilinger, 1/3 each, for experiments with entangled photons, establishing the violation of Bell inequalities and pioneering quantum information science. Read that citation carefully. It does not say they discovered that particles communicate faster than light. It says they established a violation. The prize was for closing a door, and I want to be exact about what is on the other side of that door, because this is the single most distorted result in modern physics. Entanglement does not let you send a message. The outcome on each side, taken by itself, is completely random. You cannot bias it, you cannot encode anything in it, and if you sat on one side forever, you would see nothing but noise. The correlation only appears when the two sets of results are brought together and compared, and that comparison requires an ordinary channel running at the ordinary speed of light. This is not a patch added to save relativity. It falls directly out of the mathematics, so the accurate sentence, the one worth remembering, is this. The world is non-local in what it correlates, and strictly local in what it transmits. Which means the comfortable answer is gone, and the disagreement in that survey is not a matter of taste after all. It is a set of people standing in a room where several of the exits have been bricked up, arguing about which of the remaining ones to walk through. So let us go and look at the doors. Part 6. A menu of things to give up. I want to change how you think about interpretations of quantum mechanics, and I want to do it before I list any of them. The usual framing is that these are opinions. Different physicists have different tastes. Some like one picture, some like another, and it is all a bit like arguing about music. That framing is comforting, and it is wrong. These are not opinions, they are prices. Every interpretation I am about to describe makes exactly the same prediction for every experiment that has ever been performed, every single one. If they disagreed about any measurable thing, we would have gone and measured it, and the argument would be over. They do not disagree about measurements. They disagree about what has to be true for those measurements to come out the way they do. And each one buys its agreement with the data by handing over something you currently believe. So think of it as a menu where the dishes are all identical and only the bills are different. Here is what is on offer. The first item is Copenhagen, the orthodoxy, the 36%. Its position is roughly this. A measurement produces a definite outcome. The wave function is a calculational device for predicting the odds, and questions about what happens in between measurements are not physics questions. Bohr's version was more sophisticated than that summary suggests. He had a serious argument that the properties in question have no meaning outside the context of a specific experimental arrangement, but the practical upshot for a working physicist is calculate, compare, do not ask. The bill, an unexplained unlocated split between the quantum world and the classical one. You have to have a boundary, you have to put it somewhere, and the theory will not tell you where, and per that survey, you get internal disagreement about whether the central object of your theory is even real, which is a curious thing to find inside the majority position. The second item is many worlds, which Hugh Everett proposed in 1957 while he was a graduate student. His idea was radical in its simplicity. Delete the second rule. There is no collapse. There never was. The Schrödinger equation applies always to everything, without exception. When you measure a particle in superposition, you do not cause it to choose. You become entangled with it. The superposition swallows you. Afterward, there is a version of you that saw one outcome and a version that saw the other, and each of them experiences a perfectly ordinary single world. It is worth knowing what happened to Everett. His thesis was substantially cut down before publication by his advisor, John Wheeler, who was nervous about how Bohr would react. The reception was cold. Everett left academic physics almost immediately, went to work on nuclear weapons targeting for the Pentagon, and never came back. The phrase many worlds was not even his. It was coined a decade later by Bryce DeWitt, who dug the idea up and championed it. The bill for many worlds, an ontology of unbounded size, every quantum event everywhere, always, branching, and a serious technical problem that people are still arguing about, which is where the probabilities come from. If every outcome happens, what does it mean to say one of them is 90% likely? What is being weighted if nothing is being excluded? There are sophisticated attempts to derive the answer from decision theory, and they remain contested. What many worlds buys, though, is genuinely impressive. No collapse, no non-locality, no special role for observers. One equation, applied honestly, all the way down. Its supporters will tell you it is the only interpretation that does not add anything to the mathematics, and they have a point. Third on the menu, pilot wave theory, sometimes called de Broglie-Bohm, sometimes Bohmian mechanics. Here particles are real, they always have definite positions, they always follow definite trajectories, and there is nothing fuzzy about them at all. What guides them is a real physical wave that pushes them around. The randomness in your results is simply ignorance of the starting conditions, exactly as in a coin toss. Louis de Broglie presented a version of this at the Solvay conference in 1927, was argued out of it, and abandoned it for 25 years. David Bohm rediscovered it independently in 1952, and he did so while in exile. He had refused to testify before the House Un-American Activities Committee, lost his position at Princeton, and was working in Brazil. The bill for pilot wave theory is explicit and it is heavy. The guiding wave depends instantaneously on the entire configuration of the system, everywhere. The non-locality is not hidden in the interpretation, it is written directly into the equation, and that non-locality sits awkwardly with relativity, because it seems to require a preferred notion of simultaneity that special relativity says does not exist. There is one detail here that I love, and it is a detail about how science actually works. John Bell, the man who wrote the theorem that constrains all of these theories, said explicitly that Bohm's work was what convinced him hidden variables were worth taking seriously enough to attack rigorously. Bell's theorem exists because Bohm's theory existed. The proof that killed local hidden variables was written by a man who had been persuaded, by an exiled physicist working in Brazil, that the idea deserved a fair hearing. Fourth, objective collapse. This is the family that says collapse is a real physical process, governed by an equation we have not yet written into the textbooks. I am going to give this one its own part later, because it is the only item on this menu that has been placed in serious jeopardy by an experiment, and the story of how that happened is one of the strangest things in this entire subject. Fifth, relational quantum mechanics, proposed by Carlo Rovelli in 1996. Rovelli's move is to say that there is no such thing as the state of a system, full stop. There is only the state of a system relative to another system. Different observers can hold different, equally valid accounts of the same events, and asking which one is the real one is a category error. He draws an explicit analogy with relativity. Velocity is not an absolute property of an object. It is a relation between an object and a frame, and nobody finds that upsetting anymore. He argues quantum states are the same. The bill, you give up the absoluteness of facts at the door, as a founding assumption rather than a reluctant conclusion. Remember that, because in a few parts it is going to stop being a choice. Sixth, cubism, from Christopher Fuchs, Rudiger Schack and David Mermin. The wave function is not a description of the world at all. It is a description of one agent's personal degrees of belief about what they are about to experience. Collapse is what happens when you learn something, and it is no more mysterious than updating your expectations after checking the weather. The bill here is the largest of all, and cubists pay it cheerfully. The theory stops describing the world. It describes agents in it and their expectations. Every paradox dissolves, because there was never a shared reality for the paradoxes to be about. What you surrender is the ambition that made physics worth doing in the first place. Seventh, consistent histories, developed by Robert Griffiths, Roland Omnes, Murray Gell-Mann and James Hartley. Quantum mechanics assigns probabilities to entire histories, not to instants, and you are permitted to describe a system using any internally consistent framework you like, but you are absolutely forbidden from mixing two incompatible frameworks in the same argument. The bill, multiple mutually exclusive descriptions of the same run, all correct, none preferred. Now look at that list again, and look at what is being asked of you. One world, or locality, or definite positions, or the reality of the wave function, or the idea that facts are the same for everybody, or the ambition to describe the world at all. Pick one, give it up. Because you cannot keep all of them, and you have spent every day of your life assuming all of them simultaneously without ever once being asked to choose. And I want to sit in that for a moment because I think it is the part of this subject that actually lands emotionally, once you see it. You have never had to choose. Nobody has ever asked you to. You have gone through your entire life holding, all at once, the beliefs that there is one world, that things have properties whether or not anyone is checking, that nothing here can reach out and touch something over there instantaneously, and that when something happens, it happens for everyone. Those are not four separate opinions you formed. They are the floor. They are so far beneath the level of anything you would call a belief that you have never had occasion to inspect them. And what a century of extremely careful work has produced is a list, and the list says, one of these is not true, and you may choose which. That is not the same as being told something surprising about the universe. It is being told that the room you're standing in has a load-bearing wall you cannot identify, and one of them is going to have to come down. That is the actual content of that nature survey. 1,100 people, each of whom has quietly settled on which piece of the obvious they are prepared to surrender, and most of whom, as far as anyone can tell, have never sat down and compared answers with the person at the next desk. There is one more escape route, though, and it is the one most people reach for the moment they hear all this. Just say the wave function was never real to begin with. Say it is a ledger, a bookkeeping device, a summary of our ignorance. If it never existed, it never has to collapse. In 2012, 3 physicists proved you cannot have that either. Part 7. The Theorem that said, the wave is real. Let me give the escape route its strongest form because it deserves that, and because a lot of thoughtful people have believed it. You flip a coin and cover it with your hand. Before you look, your description of the coin is 50% heads, 50% tails. You lift your hand, it is heads. Your description changes instantly, discontinuously from 50-50 to certainty. Something collapsed. But nothing happened to the coin. The coin was heads the whole time. What collapsed was a description, and descriptions live in the describer, not in the world. Nobody thinks the coin was in some blended state. Nobody demands an equation for how a probability distribution physically snaps into place. There is no measurement problem for coins, so the suggestion is simply this. What if the wave function is like that? What if it is not a physical object out in the world, but a summary of what an observer knows, and collapse is not an event but an update? Then the entire 100-year crisis evaporates. There is no jump in nature, only a jump in a ledger. The two rules were never in conflict because the first one describes the world and the second one describes learning. It is elegant. It would solve everything. And in 2012 it was shown to be, in almost all of its available forms, impossible. The paper was by Matthew Pusey, Jonathan Barrett and Terry Rudolph, published in Nature Physics under the title On the Reality of the Quantum State. What they demonstrated is precise, and it is worth stating precisely rather than in a slogan. Suppose you want the wave function to be information about some deeper underlying physical state. Fine. And suppose you want one more thing, which sounds so innocuous that it barely registers as an assumption. If you prepare two systems independently, in two separate rooms, using two separate machines that have never communicated, then those two systems have independent physical states. What happens in room 1 is not secretly entangled with the arrangements in room 2. Pusey, Barrett and Rudolph showed that if you hold both of those, you make predictions that contradict quantum mechanics. Not slightly, in a way that experiment can distinguish. It helps to see roughly how the argument runs because the shape of it is clever. Take two quantum states that are not identical, but are also not completely distinguishable. States where, if somebody hands you one and asks which it is, you cannot always tell. If the wave function is merely information, then those two states must be compatible with at least some of the same underlying physical conditions. That is what it means for them to be confusable. Sometimes the world is in a condition that either description would cover. Now prepare several such systems independently and bring them together for a joint measurement. The theorem shows there is a measurement whose possible outcomes include one that quantum mechanics says will never, ever happen, probability exactly 0, but which the information-only picture says must happen occasionally, precisely because of that overlap. Run the experiment, and quantum mechanics is right. The forbidden outcome does not occur. Physicists have a pair of words for the two positions. If the wave function is a real physical thing, the view is called psiontic, from the Greek for being. If it is a state of knowledge, it is psi-epistemic. What PBR did was not to prove psiontic. It was to make psi-epistemic enormously more expensive than it had been the day before, so one of the two must go. And giving up the second one is far more expensive than it looks at first glance, because preparation independence is the assumption underneath every controlled experiment ever conducted. It is what lets you say, I made this thing here, and it does not know about anything happening over there. Without it, science does not have a method. The practical result is that the comfortable phrase, it is just information, no longer buys you what people thought it bought. Some carefully constructed positions survive PBR. Cubism survives by refusing the premise that there is an underlying physical state at all. Relational quantum mechanics survives by refusing that there is a single one. But the casual version, the one most people mean when they wave it away, does not survive. There is a companion result that deserves a sentence because it closes a different door. In 1967, Simon Koshun and Ernst Specker proved that you cannot consistently assign pre-existing values to all quantum properties in a way that is independent of what else you choose to measure alongside them. Not because of distance, this is not about locality, but because the values themselves would have to depend on the company they are measured in. Physicists call this contextuality. It means that even in one small laboratory, with nothing far away, the idea that every property has a value waiting to be read is untenable. And notice how different that is from Bell. Bell's result is about two places. It can be blamed, if you like, on distance and connection. Koshun and Specker need no distance at all. Their result says the trouble is already there in a single system, on a single bench, in a single instant. Whatever a quantum property is, it is not a number written on a card waiting for someone to turn it over, and that is true before you introduce any second location for anything to be spooky across. Now let me stop and put everything on the table, because we are at the halfway point and I want to make sure the pieces are stacked. We started with a survey. 1,100 physicists, no agreement, and the largest group not even agreeing with itself. We went into the box and found that superposition is not hidden information, but genuine indeterminacy, evidenced by interference stripes that vanish the instant anything records which way the thing went. We found the theory has two incompatible rules and no equation to say when to switch. We watched Schrödinger build an apparatus to make that absurdity visible and watched his complaint get adopted as a mascot. We cut down through atoms to quarks to fields and found nothing at the bottom that could possibly be doing the deciding. We watched Bell turn 30 years of philosophy into arithmetic and watched two experiments, one in a Dutch building at 3 a.m, one using light older than the solar system, close the last cracks in that arithmetic. And we laid out the surviving interpretations as a menu of things you must give up. And here is the pattern that comes out of the restack, the thing I did not see until I put it in this order. Every exit from this problem is a door that somebody has already walked through and found bricked. Hidden variables, bricked in 1964, confirmed in 2015 and 2018. Values waiting to be read, bricked in 1967. The wave function as mere information about something deeper, bricked in 2012. What is left standing is a small set of options, and every one of them is expensive, which changes the meaning of that survey completely. When a physicist says the choice between interpretations is a matter of taste, They are saying something true and something misleading at the same time. True. No experiment distinguishes the survivors. Misleading. The survivors are survivors. They are what is left after 60 years of systematic demolition, and the field of options has been narrowing the entire time in one direction, toward stranger, not toward more familiar. There is a temptation, when you hear a list of things that have been ruled out, to assume the ruling out was done by people who wanted the strange answer to win. It was the opposite, every time. Bell was trying to give hidden variables their fairest possible hearing. Clauser expected local realism to be confirmed. The Delft group spent 9 days chasing 245 events, specifically so that no one could accuse them of cherry-picking. Every one of these results was produced by somebody attempting in good faith to close a door on the weirdness, and every one of them ended up closing a door on the alternative instead. That is the terrain those 1,100 people are standing on. It is not a garden of equally pleasant possibilities. It is a corridor, and it has been getting narrower, and the exits behind them are sealed. But I have been holding something back, and you have probably been thinking it for the last 20 minutes. All of this is about atoms and photons and things too small to see. Whatever is going on down there, it does not seem to leak upward. My coffee cup does not interfere with itself. My keys are always in one place, admittedly not always the place I left them. The world at my scale is stubbornly, boringly definite. So why is that? What actually protects you from all this? There is an answer. It is one of the genuine triumphs of a late 20th century physics. It is correct, it is beautiful, and almost everyone who repeats it gets one crucial thing about it wrong. Part 8. Why you never see the cat. The answer is called decoherence, and I want to give it full credit before I start qualifying it, because this is not a dodge or a hand wave. It is one of the genuine achievements of the last 50 years of physics. It is worked out in mathematical detail, it has been tested, and it explains something that used to look completely mysterious. Here is the idea. A quantum system in a superposition stays in a superposition only as long as it is left completely alone. And nothing in your world is left completely alone. Not for an instant. Every object around you right now is being continuously touched. By air molecules bouncing off it, by photons of light landing on it, by infrared radiation from every warm surface in the room, by the faint microwave glow left over from the Big Bang, which is still arriving, everywhere, all the time. Every single one of those touches carries information away. When an air molecule bounces off an object, the direction it leaves in depends on where the object was. That molecule is now a tiny, terrible, one-bit witness. It has recorded something. And remember what we established with the interference stripes. The moment which path information exists anywhere in the world, the fringes vanish. It does not matter whether anyone reads the information. It does not matter whether the air molecule is conscious, which I assume it is not. What matters is that the record exists. So let me put you in the room where this happens. There is a sunbeam coming through a window, and hanging in it, turning slowly, is a speck of dust. About 1/100th of a millimeter across. Just barely something your eye can catch when the light hits it right. Suppose you could put that speck into a superposition of being in two slightly different places at once. And suppose you could start a clock at the instant you did it. The air arrives. Not gently. There are something like 10 to the 19th air molecules in a cubic centimetre at room temperature, and they are moving at hundreds of meters per second. They arrive constantly from every direction, and each collision writes down a little of where that speck is. How long does the superposition last? About 10 to the minus 31 seconds. I need to give you something to hold it against because a number like that is meaningless on its own. In 10 to the minus 31 seconds, light, the fastest thing there is, travels a distance far smaller than a proton, not a smaller fraction of a proton, far smaller, something like a trillionth of a proton's width. That is how long your dust speck gets to be in two places before the room takes it away. And if that seems like a cheat because a dust speck is a big object, run it downward. Take a large molecule instead, and the time stretches out to something a laboratory can work with. Take a single atom in a good vacuum chamber, shielded from stray light, and it stretches out to seconds. The physics does not change, only the number of witnesses does. That calculation was done in the mid-1980s by Erich Jüss and Dieter Zeh, and it is still one of the most clarifying results in the subject. For macroscopic objects, the general range runs from about 10 to the minus 18 seconds down to 10 to the minus 31, depending on the object and what is hitting it. Put an object in a perfect vacuum in total darkness at absolute zero, and the time gets longer. Put it in a room, and it is over before anything can be said to have begun. So here is the sentence I want you to keep. The barrier between the quantum world and your world is not a wall. It is a rate. There is no size at which superposition is forbidden. There is no line drawn across the periodic table, with quantum on one side and classical on the other. There is only how fast the surroundings write down what happened, and for anything big enough to see, the surroundings are extraordinarily fast writers. The physicist who developed this furthest is Wojciech Zurek at Los Alamos, and he added two ideas that make the picture much richer than simply the environment ruins it. The first is what he calls einselection, environment-induced superselection. The environment does not damage superpositions indiscriminately. It selects. Some states survive being copied into the surroundings, and some do not, and which ones survive is determined by how the system interacts with what is around it. The survivors are called pointer states, named for the pointer on a measuring instrument, and they are the states you find things in. A dust speck has a definite position rather than a definite momentum, because position is what the air molecules keep writing down. The classical properties of the world are not arbitrary. They are the states that are good at leaving copies of themselves. The second idea is stranger and more beautiful, and Zurek calls it quantum Darwinism. Ask yourself why objective facts feel objective. Why can you and I both look at the same table and agree it is there, without either of us disturbing it or each other? Zurek's answer is redundancy. The environment does not make one record of the table. It makes an enormous number in independent fragments. Every scattered photon carries a copy. You intercept one fragment with your eyes, I intercept another with mine, and we both learn the same thing, and neither of us has to touch the table or negotiate with the other. Objectivity in this picture is not a basic feature of reality. It is what happens when a fact has been copied so many times that everyone can have their own. That idea got its first experimental test in 2019 from 3 independent groups working with completely different systems: a photonic quantum simulator, nitrogen vacancy centers in diamond, and photonic cluster states. All 3 saw roughly what the theory predicts. The information about a system does proliferate redundantly into the environment, and it does so in the pattern quantum Darwinism describes. So there it is, a complete, tested, mathematically detailed account of why you never see a cat in a superposition, why your keys are always in one place, why the world at your scale is so relentlessly ordinary. And now I have to take it away from you. Because decoherence does not solve the measurement problem. It solves half of it, and the half it solves is the easier half. Here is what the mathematics actually does. You start with a system in a superposition of 2 states. The environment interacts with it. What you end up with is not one of the 2 states. What you end up with is an entangled state of system plus environment, in which both branches are still fully present in the equations, still there, just no longer able to interfere with each other because the information distinguishing them has been spread across 1 trillion air molecules and can never practically be gathered back. Both branches, still there. It is worth being very clear about the sleight of hand that happens in popular accounts, because it is almost always the same one. Somebody explains decoherence and then says, and so the superposition is destroyed. It is not destroyed. It is delocalized. The difference matters enormously. If I take a written confession and shred it, the confession is gone. If I take a written confession and photocopy it 10 trillion times and scatter the copies across the surface of the earth, nothing has been destroyed at all. But you will never reassemble the original, and for every practical purpose the document has stopped behaving like a document. Decoherence is the second thing. It is the most thorough scattering process in nature, and it is not a deletion. Decoherence explains, completely and rigorously, why you cannot observe the interference. It says nothing whatsoever about why you observe one outcome. It takes a superposition of alive and dead and turns it into a superposition of alive and dead and thoroughly documented, and then it stops, because that is all the Schrödinger equation can do. The equation is linear. It cannot delete a branch. It has never been able to delete a branch, and the entire content of the measurement problem is that something, somewhere, appears to delete a branch. Every serious review of this subject is explicit about the limitation. The 59-page survey of the measurement problem published in 2025 is explicit about it. This is not a fringe caveat. This is the standard, uncontroversial understanding of what decoherence does and does not accomplish. So the best answer physics has answers a question the survey was not about, which leaves one obvious line of defense still standing. Fine, you might say. Maybe the equation cannot delete a branch, but so what? All of this concerns objects small enough for the argument to be academic. Nobody has ever put anything remotely substantial into two places at once. About that. Part 9. How big can two places at once get? This is the question that turns the whole subject from a philosophical irritant into an experimental program, and I love it because it is such a simple, stubborn, almost childish thing to ask. Fine. You say superposition is universal. You say there is no wall, only a rate. Prove it. Take something bigger and put it in two places. So people did, and they have been getting steadily better at it for 30 years, and the numbers are genuinely startling. The tool is called matter wave interferometry, and in principle it is the same experiment we talked about earlier with the two openings and the stripes on a screen. In practice, doing it with anything larger than an electron is brutally difficult, for the reason we just established. The bigger the object, the more furiously the environment writes down where it is. You have to run in a hard vacuum, you have to keep everything cold, and you have to complete the entire journey before a single stray gas molecule ruins it. There is also a subtler problem. To get clean interference from a beam of anything, you normally need the beam to be very well behaved. Narrow, monochromatic, prepared in a tidy state. You cannot do that with a big molecule. Big molecules come out of an oven in a chaotic spray, tumbling, vibrating, rotating with a wide spread of speeds. For decades that looked like a hard limit. The way around it is a design called a Talbot-Lowe interferometer, and its virtue is that it works with a messy, broad source. Instead of demanding a coherent beam, it uses a sequence of gratings, and the second grating effectively re-establishes the coherence the source never had. Each molecule interferes with itself, individually, and the pattern builds up statistically from an enormous number of separate chaotic arrivals. It is a machine designed for the real world, which is why it has been able to keep scaling up. In 2019, a group at the University of Vienna, led by Jakob Fein and Marcus Arndt, published the current landmark. The instrument was 2 meters long, and the objects they sent through it were molecules called functionalized oligoporphyrins, with masses beyond 25,000 daltons, containing up to 2,000 atoms each. 2,000 atoms, in two places at once, and they stayed that way for more than 7 milliseconds. 7 milliseconds does not sound like much, but hold it against something. It is roughly the exposure time of a fast camera shutter. It is more than twice as long as a hummingbird's wing beat. For 7/1000ths of a second, an object made of 2,000 atoms had no answer to the question of which route it took. There is a detail here that I find quietly wonderful. Those molecules did not exist in nature. Chemists synthesized them specifically for this experiment, designed them to be heavy but stable, to survive being launched, to not fall apart in flight. A team of chemists spent years building an object so that a team of physicists could put it in two places at once. That is a sentence that would have been incomprehensible a century ago, and it describes a normal Tuesday in Vienna. 25,000 daltons puts these molecules in the size range of a small protein, which is to say, the current record for two places at once is in the size range of biological machinery. Not a cell, not close to a cell, but the components a cell is built out of. It is worth walking the ladder because the climb is the argument. In 1927, Clinton Davison and Lester Germer showed interference with electrons, a single particle, about as light as matter gets. Neutrons followed, then whole atoms in the 1980s. Then, in 1999, the Vienna group put a buckyball through, 60 carbon atoms locked into a soccer ball cage, an object with internal structure, internal temperature, internal vibrations, an object that is unambiguously a thing rather than a particle, then molecules of a few hundred atoms, then 1,000, then 2,000. Notice that nothing dramatic happened at any point on that ladder. There was no rung where the effect got weaker, no threshold where the stripes started to fade for reasons other than the apparatus. Every step up was harder for engineering reasons, better vacuum, better cooling, better isolation, and every step up worked. 60 years of people climbing, expecting at some point to find the ceiling, and finding only that the next rung required a better ladder. Now here is the second front, and it comes at the problem from a completely different direction. In 2021, a team at the National Institute of Standards and Technology in Boulder, Colorado, led by Shlomi Kotler and John Teufel, published a result in Science. They were not doing interferometry. They were working with mechanical objects, two tiny aluminium membranes, drumheads, each a few micrometers across, cooled to a whisper above absolute zero and driven with pulsed microwaves. Each drum weighs about 70 picograms. 70 picograms is roughly the mass of a small bacterium. It is an object. Not a hypothetical object, not a mathematical idealization, a physical component, machined, mounted, sitting in a cryostat containing something like 1 trillion atoms, and they entangled 2 of them, deterministically. That word matters more than it sounds. In a great many quantum experiments, the interesting result happens rarely and you fish it out afterward by keeping only the runs where things went well. That is called post-selection, and critics can always ask whether the selection created the effect. Kotler and Teufel's experiment did not need it. They pressed the button and the drums came out entangled, on demand, and every necessary quantity was directly measured rather than inferred. Physics World named it one of the breakthroughs of the year, and the reason was precisely that lack of caveats. 2 objects, 1 trillion atoms each. Their motions correlated in a way that no classical description can account for, exhibiting exactly the property Einstein spent his last decades objecting to. And I want to point out how differently those 2 experiments attack the same question. The Vienna group took one object and made it exist along 2 paths. The classic strangeness, superposition, one thing in 2 places. The Boulder group took 2 objects and made them share a description they could not have separately. Different phenomena, different equipment, different physics communities, and neither one has anything to do with the other, except in the only respect that counts here. Both of them are quantum behavior, in objects, at scales, where the textbook reassurance said it should have stopped. So let us total up what has happened to the comfortable defense. The defense was, this is only true of things too small to matter. In 2019, that boundary moved to 2,000 atoms in genuine superposition. In 2021, it moved to 1 trillion atoms in genuine entanglement. Both of those numbers are less than a decade old. Both of them are limited by engineering, by vacuum quality, by cooling, by vibration isolation, and not by any known physical prohibition. Every year, the machines get quieter and the objects get bigger. There is a research program built entirely around pushing further, and its stated ambition tells you how seriously the field takes this. People are working on levitating nanoparticles in optical traps and cooling them to their motional ground state, on interference experiments with objects 1,000,000 times heavier than the current record, on proposals to test whether 2 masses can become entangled through nothing but their mutual gravity, which, if it worked, would show that the gravitational field itself has to be quantum. None of these is science fiction. All of them are funded, staffed, and being built by people who fully expect them to work. There is no known upper limit. That is the honest statement of the situation. Nobody has ever found the place where the theory stops working, and every time somebody has gone looking for a boundary, they have found instead a technical difficulty they eventually solved, which means the wall you were relying on has moved twice in 6 years, in the same direction, and nothing in our current understanding says where it stops, unless, of course, somebody adds a new law. And that is exactly what a group of physicists proposed. They wrote down an extra term, a new physical process, an actual mechanism that would forbid large superpositions rather than merely making them hard to see. It was the most physically conservative, most sensible, most satisfying answer anybody has ever offered to the measurement problem. It has a beautiful equation. It makes the cat problem disappear. And because it makes a genuine prediction, because it is, unlike everything else on the menu, an actual different theory of the world, it can be tested. So somebody tested it, under a mountain in Italy, and what they found there is one of the quietest and saddest results in modern physics. Part 10. The model that would have saved us. Suppose you're a physicist in the 1980s and you have had enough. You look at the measurement problem and you notice something. Everybody is trying to explain the second rule away, to argue that collapse is an illusion, or an update of knowledge, or a branching, or a matter of perspective. And you think, why? Why is everyone so determined that the second rule cannot be real? Maybe collapse actually happens. Maybe it is a physical process, like radioactive decay is a physical process, and the only reason we have no equation for it is that nobody has bothered to write one. So you write one. In 1986, 3 Italian physicists, Giancarlo Ghirardi, Alberto Rimini, and Tullio Weber, published exactly that, in Physical Review D under the wonderfully plain title, Unified Dynamics for Microscopic and Macroscopic Systems. The model is now called GRW after their initials, and it is, in my opinion, the most elegant thing anyone has ever proposed in this field. Here is how it works. Every particle in the universe has a tiny, spontaneous, utterly random chance of suddenly localizing, of having its wave function abruptly narrowed down to a small region. It happens for no reason. Nothing triggers it. It is a fundamental process like decay. The rate they chose is roughly one such event per particle per 100 million years. Now at first that sounds useless. 100 million years? A single electron will essentially never localize. You could watch one for your entire life and nothing would happen. Which is exactly right, because single particles are precisely the things we observe in superposition, routinely, in laboratories. The model must not disturb them, and it does not. But now think about a cat, or a dust speck, or a drumhead. The particles in a macroscopic object are not independent. They are bound together. If one particle in a cat suddenly localizes, the whole cat comes with it, because you cannot have the nose in one place and the rest of the face somewhere else. So the effective rate for the whole object is the individual rate multiplied by the number of particles. And a cat contains something on the order of 10 to the 27th particles. Multiply one event per 100 million years by 10 to the 27, and the cat localizes in something like a 10 millionth of a second. Instantly, for any practical purpose. Look at what that achieves. One equation, one new fundamental process with two constants in it, and the entire measurement problem dissolves. Small things stay in superposition because their collapse rate is negligible. Large things do not because their collapse rate is enormous. There is no observer. There is no consciousness. There is no shifty split, no boundary anyone has to draw, no philosophical argument about what counts as a measurement. The cat is dead or alive within a microsecond of the vial breaking, and nobody had to look. That is what a solution looks like. That is what physics is supposed to produce. There is one more feature of the model worth mentioning, because it shows how carefully it was built. The localization is not perfectly sharp. When a collapse happens, the wave function is narrowed to a region of a particular width. GRW put it at around a 10 millionth of a meter. That number is not arbitrary either. Make it much smaller and the sudden narrowing injects too much energy, and matter would visibly heat itself up for no reason, which we would have noticed. Make it much larger and it fails to localize a cat properly. There is a window, and they aimed for the middle of it. Two numbers, chosen to make the model invisible where quantum mechanics works and decisive where it does not. There are relatives of GRW. The most studied is called continuous spontaneous localization, which smooths the sudden jumps into a continuous stochastic process. And there is a version from Roger Penrose and from Laios Diossi independently, which is the most ambitious of all, because it does not invent a new process out of nothing. It says gravity does it. The Diossi-Penrose idea is that a superposition of two mass distributions is a superposition of two different spacetime geometries, and that spacetime cannot sustain that indefinitely. The bigger the difference in mass distribution between the branches, the faster the collapse. The elegance is that the collapse time is set by the gravitational self-energy of the difference, which means there is nothing to tune, no free parameter, gravity supplies the number, and a theory with no free parameter is a theory you can kill. Because here is the thing about all collapse models. Unlike every other item on that menu, they are not interpretations. They are different physical theories. They predict something quantum mechanics does not, and that prediction is this. If particles are being randomly jostled by spontaneous localization events, and those particles are charged, then they must radiate. Accelerating charges emit photons. It is one of the oldest results in physics, so the collapse is not invisible after all. It should glow, very faintly. Absurdly faintly. But if you build a detector sensitive enough and you shield it well enough from everything else that produces photons, you should be able to see the universe collapsing. So somebody went looking. Underneath the Apennine Mountains in central Italy, there is a laboratory. It sits beside a motorway tunnel, roughly 1,400 meters below the summit of the Gran Sasso Massif, and it exists because that 1,400 meters of rock is the best shield available on this planet. Cosmic rays that would drown any delicate measurement on the surface are suppressed by a factor of about 1,000,000 by the time they reach the halls down there. Picture it. You are inside a mountain. There is no daylight and there never has been. In a shielded chamber there is a block of ultra-pure germanium, cooled, watching. And what it is watching for is nothing in particular. No beam, no source, no experiment being run at it. It is simply listening to a piece of matter in the dark to hear whether it makes a sound as it collapses. In 2020, Sandro Donardi, Christian Pichicchia and their colleagues published what it heard in Nature Physics. It heard less than the theory requires. The photons predicted by the parameter-free version of the Diossi-Penrose model, the version where gravity does it and there is nothing to adjust, were not there. Not fewer than expected. Not marginally low. Absent, to a level about 3 orders of magnitude beyond any previous constraint. The natural parameter-free Diossi-Penrose model is ruled out. There is something almost mournful about that result, and I do not think that is an overstatement. Penrose's version was the most beautiful idea in the entire field. It connected the two great unreconciled theories of 20th century physics, quantum mechanics and general relativity, and it said the tension between them is not a problem to be solved but the mechanism itself. Gravity does not merely resist being quantized. Gravity is what stops the quantum world from running away with everything. It explained the measurement problem using something we already knew existed, with nothing invented, nothing adjusted, and no free numbers to fit. If the universe had been designed by someone with taste, that is how it would have worked. It did not work. I want to be careful and fair here, because the collapse program is not dead. You can save versions of these models by introducing a smoothing length, by tuning parameters, by making the collapse gentler in specific ways. Continuous spontaneous localization is still alive, but it is being squeezed from both sides at once, by the interferometry we just discussed, which pushes superpositions to larger and larger masses where collapse should have kicked in, and by radiation searches like this one, which look for the signature directly. The window of surviving parameters gets smaller every year, and now I want you to see the shape of what has happened, because it is genuinely perverse. There is a menu of options for what quantum mechanics means. Almost all of them make no new predictions. They cannot be tested, they cannot be refuted, and so they will survive indefinitely, forever, exactly as they are, no matter how many experiments anybody runs. There is one family on that menu that does make new predictions, one family that stuck its neck out and said, here is a real physical process, go and look for it, and that is the family currently being eliminated. Not because it was worse, because it was braver. It offered a mechanical answer to the question at the heart of all of this. Why does one thing happen instead of another? And the price of offering that answer was that the answer could be checked, and when it was checked in the dark under a mountain, it was not there. So physics is being pushed toward unfalsifiability, not by preference, not by laziness, not by some failure of nerve, by results. The testable options are being tested and are dying, and what remains standing is precisely the set of ideas that no experiment can touch. Which means the mechanical exit is closing, and the only thing left is the interpretive one, and that is where the last 8 years have produced something genuinely new. Because it turns out you do not need a cat to make this unbearable, you only need a friend. Part 11. Wigner's friend walks out of the lab. In 1961, Eugene Wigner, a Nobel laureate, one of the great mathematical physicists of the century, took Schrödinger's cat and made one small change to it. He replaced the cat with a colleague. That is the entire modification. Instead of an animal in a steel chamber, you have a competent physicist in a sealed laboratory. Call her the friend. Inside her lab there is a quantum system in a superposition and a measuring apparatus, and she runs the measurement. She watches the needle. She sees a result. She writes it down in her notebook, and outside, in the corridor, is Wigner. He has not opened the door. He has not received any signal from inside, and from where he stands, the entire laboratory, the system, the apparatus, the notebook, and the friend, is one big closed physical system that has been evolving under the Schrödinger equation the whole time. Nothing has interrupted it. So by the rules, the correct description of the contents of that room is a superposition. A superposition of a physicist who saw one result and a physicist who saw the other. Let me put you inside the room. You are the friend. The lab is small and quiet. You have run this measurement 100 times before. You watch the apparatus and the needle swings left and you note it down, and it is the most ordinary thing in the world. A fact, recorded at a specific time by you. There is nothing ambiguous about it from where you're sitting. You saw what you saw, and on the other side of that door is a colleague who does not think you saw anything yet. Not because he is being difficult, because the equations he is using, The same equations you use, the ones you both trust completely, the ones neither of you has ever seen fail, describe you as undecided. And this is not merely a philosophical stance he could drop if he wanted to. In principle, if he had the technology, he could perform an interference measurement on the entire room and get a result that is only possible if what you experienced did not definitely happen. Your certainty is inside the box, his description is outside it, and the box has not decided yet. That is the same sentence I gave you earlier when it was small and charming and there was an apple inside. It is the same sentence. Nothing about it has changed except what is in the box, and what is in the box now has a heartbeat and a notebook and a memory of the needle swinging left. There is a standard reply to all of this, and it is worth taking seriously because it is the first thing any sensible person says. Surely this is absurd on practical grounds. A laboratory containing a human being is not an isolated quantum system in any realistic sense. It is warm, it leaks heat and light and sound. It is in contact with the ground, with the air, with the rest of the building. Decoherence would flatten a superposition of that room faster than any clock could measure. Nobody will ever perform Wigner's interference measurement on an actual person, and everybody involved knows it. All true. And it does not help for the same reason the cat did not help. The question was never whether we can do the experiment. The question is what the theory says, and the theory says the isolation is a matter of degree. There is no principle forbidding it, only a practical difficulty that gets more difficult with size. And we spent the whole of the last part watching people shrink that difficulty, decade by decade, from an electron to a buckyball to 2,000 atoms to a trillion. If the only thing standing between you and the paradox is engineering, then what you have is not an argument. What you have is a deadline. For nearly 60 years this stayed exactly where Wigner left it. A provocation, a philosopher's toy, the kind of thing you argue about after a conference dinner. Then, over the last 8 years, 3 things happened in quick succession that turned it into hard result. The first was in 2018. Daniela Frauschiger and Renato Renner at the Swiss Federal Institute of Technology in Zurich published a paper in Nature Communications with a title that is itself the finding. Quantum theory cannot consistently describe the use of itself. What they built is an extended version of Wigner's setup with 4 agents, 2 friends in 2 sealed laboratories and 2 outside observers. Every agent is treated as a physical system evolving unitarily. No collapse is invoked anywhere in the argument, not once. And then each agent uses quantum mechanics to reason not just about particles, but about what the other agents will conclude. Agent 1 reasons, given what I observed, Agent 2 must have concluded such and such. Agent 2 reasons about Agent 3, and so on. Following the rules correctly, with no errors, the agents arrive at flatly contradictory statements about the same experimental run. One of them concludes with certainty that the answer is yes. Another concludes with certainty that it is no. I want to be precise about what that does and does not show, because it gets overstated constantly. It does not show that quantum mechanics makes a wrong prediction. Every individual prediction in the setup is fine. What it shows is that you cannot simultaneously hold 3 things. That quantum theory applies universally, including to observers, that different agents' conclusions can be chained together into a single consistent account, and that a measurement has exactly one outcome. At least one of those has to be abandoned, and every interpretation on that menu abandons a different one. Many worlds gives up the single outcome. Copenhagen, in most readings, gives up the universal applicability. Cubism and relational quantum mechanics give up the chaining, the idea that your conclusions and mine can be combined into one story. The Frauschiger-Renner paper actually includes a table sorting the interpretations by which assumption each one drops. They hand you the menu with the prices already written in. The second thing happened the following year, and it moved this out of the realm of argument entirely. In 2019, Massimiliano Proietti, Alessandro Fedrizzi, and colleagues at Heriot-Watt University in Edinburgh built one. Obviously they did not seal a person in a room. What they did was construct a scenario with the same logical structure using 6 photons, where a photon plays the role of the friend. It performs a measurement, in the sense that it becomes correlated with the system in exactly the way a measuring device does, and it produces a record. Then they measured the whole thing from outside, the way Wigner would. The results violated the associated inequality by 5 standard deviations. Their conclusion, stated plainly in Science Advances, is that if you want to hold on to locality and to the free choice of your measurement settings, then quantum theory has to be interpreted in an observer-dependent way, not as a metaphor, as what the data says. And then, in 2020, came the third piece, and it is the one that I think should genuinely unsettle you. Cockway Bong and colleagues at Griffith University in Australia published a paper in Nature Physics that took this whole line of argument and turned it into a formal no-go theorem in the same rigorous style as Bell's. They defined a set of assumptions and gave it a name: local friendliness. Local friendliness has two components. The first is local agency, the ordinary requirement that an intervention here cannot influence events outside its future light cone. Nothing controversial about that. It is relativity. The second one is called the absoluteness of observed events, and what it says is this: an event observed by any observer has an absolute value rather than a relative one. That is it. That is the whole assumption. When something happens, it happened. Not for you, not from a point of view, not in a frame. It happened. Quantum mechanics violates local friendliness, and the constraint is strictly stronger than Bell's. There exist correlations that satisfy Bell's inequality and still violate this one. It cuts deeper. I need you to sit with the shape of that, because I do not think there is anything else in physics quite like it. Bell's theorem told us we could not have both locality and predetermined values. That was hard enough. People had to give up the idea that particles carry their properties around with them. Local friendliness tells us we cannot have both locality and the absoluteness of observed events. Not properties, not positions, not spin or momentum or which slit it went through. Events. The claim that something happened. In 2020, a group of physicists took the sentence "this really happened," wrote it down as a formal premise in a mathematical theorem, gave it a name, and proved that it is one of the assumptions that has to go. Think about what depends on that sentence. Every court that has ever heard testimony, every memory you trust, every scientific record, every logbook, every photograph, every witness. The entire architecture of shared human knowledge is built on the assumption that when an event occurs, it occurs once for everybody, and that if you and I disagree about it, at least one of us is wrong. Physics does not currently guarantee that. It has, over the last 8 years, produced a theorem saying you may not keep it and locality at the same time, and an experiment in Edinburgh showing that the universe does the thing the theorem describes. This is the flaw underneath that survey. This is what those 1,100 physicists are standing on when they tick a box marked Copenhagen, or many worlds or no preference. And most of them, as far as anyone can tell, have never sat down with the person at the next desk and asked which one of these they have quietly agreed to live without. And notice one more thing before we move on, because it is the detail that stops this being purely abstract. The Edinburgh experiment did not need a conscious friend. It used a photon, and it worked, because what matters for the argument is not awareness but the existence of a record. The friend, in the mathematics, is anything that registers an outcome, which means the paradox does not live at some exotic boundary where mind meets matter. It lives wherever information is recorded, which is everywhere, constantly, in every detector and every dust grain and every retina in the universe. There are two ways out. I want to show you both of them honestly because they are real, and I want you to notice that neither one is a place you would choose to go. Part 12. The two doors still open. The first door has been sitting there, unlocked, since 1964, and almost nobody wants to walk through it. When John Bell wrote his theorem, he had to make some assumptions, and he was scrupulous about listing them. One of them is so quiet that it usually gets read past entirely. It is called statistical independence, and what it says is that the hidden properties of the particles you are measuring are uncorrelated with the settings you choose on your detectors. In plain language, what you decide to measure has nothing to do with what is there to be measured. That sounds less like a physical assumption than a description of how thinking works. But it is an assumption. It is doing enormous load-bearing work, and if you deny it, Bell's conclusion does not follow. Deny statistical independence and you can have a theory that is local, deterministic and realist, all three at once. The full classical package, everything Einstein wanted restored. The position is called superdeterminism, and it has spent 60 years as the option nobody takes seriously. In 2020, Sabine Hossenfelder and Tim Palmer published a paper in Frontiers in Physics arguing that the dismissal has been too quick. Their case is that violating statistical independence does not require a cosmic conspiracy, which is how it is usually caricatured. It requires only that the state of your detector and the state of your particle are not fully independent of each other. And in a universe where everything has been interacting with everything else since the beginning, they ask, why on earth would you expect them to be? Palmer's version connects it to a specific geometry, in which the physically possible states of the universe form a fractal set, and the combinations Bell's argument requires simply are not on it. I said the door was unlocked, not that it was inviting. The price is severe, and Hossenfelder is honest about it. If what you choose to measure is correlated with what you are measuring, then controlled experiment, the method underneath all of science, is compromised in principle. You can never be certain your sample was fair, because the thing that picked your sample knew about your sample, and remember what the astronomers did about this. That is what the quasar experiment was for. When they set their measurement angles using light emitted 7.8 billion years ago, they were pushing the required correlation back beyond the formation of the solar system. Superdeterminism technically survives that, but only by accepting that the correlation was laid down at the Big Bang and has been waiting patiently for a laboratory in Vienna. There is one thing in superdeterminism's favour that its critics tend to skip, and fairness requires saying it. It is, at least in principle, testable. Hossenfelder has proposed concrete signatures. If the hidden variables are physical quantities that need time to settle back down after being disturbed, then measurements repeated faster than that settling time should show correlations between successive outcomes. Sequences that are supposed to be perfectly random should show a faint structure in time. Nobody has looked carefully. That is a strange thing to be able to say about an idea that has been dismissed for 6 decades. The experiment is not expensive, and it has not been done. Some people find that beautiful. Most find it unbearable. Either way, notice the pattern that has held all the way through this. Every remaining exit costs you something you currently believe, and this one costs you the reliability of experiment itself. Now the second door, and it is the one you have probably been waiting for. Go back to Wigner's friend and ask where the chain actually stops. The atom, the detector, the apparatus, the notebook, the friend's eye, her optic nerve, her brain. John von Neumann proved in 1932 that you can place the boundary anywhere along that chain, anywhere at all, without changing a single prediction. And Wigner, for a period, argued that the only non-arbitrary place to put it is at the very end. At the moment the information enters a mind, consciousness causes collapse. It is the oldest of the interpretations and easily the most famous outside physics, and I should tell you plainly that almost no working physicist holds it. The surveys bear that out. It barely registers, and the reasons are good ones. It makes physics depend on a phenomenon nobody can define. It offers no equation, no rate, no threshold. And it implies the universe had no definite history until something woke up in it, which is difficult to reconcile with the fact that we can read that history in rocks. There is a related proposal that runs the arrow the other way, and it is worth separating carefully because people constantly confuse the two. Roger Penrose and Stuart Hamroff's orchestrated objective reduction does not say consciousness causes collapse. It says collapse causes consciousness. It takes the gravitational collapse mechanism we discussed earlier and locates it in quantum vibrational states inside microtubules, the structural filaments in neurons. Consciousness, on this view, is what a sequence of these collapse events feels like from inside. It has been attacked for 30 years, and the central objection is the one you would expect. A brain is warm and wet and noisy, and decoherence there should be catastrophically fast, vastly faster than anything a thought could use. In 2024, a group led by Michael Wiest at Wellesley published a result in a neuro that is at least interesting. They gave rats a drug called apothylone B, which binds to and stabilizes microtubules, and then anesthetized them with isoflurane. The treated rats took, on average, 69 seconds longer to lose consciousness. I am going to give that exactly the weight it deserves and no more. It is one study, in rats, with a specific drug, and it does not demonstrate quantum effects in the brain. What it does is make a prediction from an unpopular theory and find the predicted direction. That is the beginning of a conversation and not the end of one, and anyone telling you it proves the brain is a quantum computer is selling something. It is worth noticing why this door keeps getting opened by people outside physics, because the reason is instructive. The word observer, in quantum mechanics, is a technical term, and it means anything that records information. A photographic plate is an observer. A dust grain is an observer. The interstellar medium is a spectacularly effective observer, which is why superpositions do not survive in nebulae any better than they survive in your kitchen. But the word has an everyday meaning too, and the everyday meaning has a person in it, and 100 years of popular writing has quietly slid from one to the other. Almost every claim you have ever encountered about consciousness creating reality traces back to that single slippage between two meanings of one badly chosen word. Two doors, then. One costs you the reliability of controlled experiment. The other costs you the idea that physics is about the world rather than about minds, and is supported by almost nobody who does this for a living. I have shown them to you because they are genuinely open, and it would be dishonest to pretend otherwise. But look at where we now are. The comfortable answer is gone. The mechanical answer is being eliminated under a mountain. The remaining interpretations each demand a payment. The exits are two, and neither leads anywhere anyone wants to live. So what is left? What is the thing at the bottom of this? The one that 100 years of extraordinary people have circled and not said out loud? Let me tell you. Part 13. What the universe owes you. Here is the answer. I am not going to make you wait for it any longer. The most terrifying quantum reality that scientists do not even want to talk about is not many worlds. It is not that there are copies of you branching off constantly, living lives you will never see. That idea is unsettling in a science fiction way, but it is a big, dramatic, cinematic strangeness, and human beings are actually rather good at absorbing those. It is not the cat either. The cat is a teaching device. Nobody has lost sleep over the cat since about 1950. The terrifying thing is smaller than that and much closer in. It is this. When something happens, it may not be true that it happened. Not happened for you. Not happened as far as you can tell. Happened. Full stop. No qualifier. No observer attached. That sentence, the plainest sentence in the language, the one underneath every other sentence, may not be the kind of thing that can be true, and this is not a mood. It is not a philosopher's flourish. In 2020, a group of physicists in Australia wrote that assumption down formally, called it the absoluteness of observed events, and proved that you cannot keep it together with locality. The year before, a team in Edinburgh built a working version of the scenario with 6 photons, and watched the universe do exactly what the theorem said it would, to 5 standard deviations. That is the first half of the answer. Here is the second half, and it is the half that makes it genuinely hard to live with. You cannot find out which story is true. The interpretations that survive, many worlds, pilot wave, relational, cubist, Copenhagen, consistent histories, make identical predictions for every experiment that has ever been performed or that anyone currently knows how to perform. They are not different theories waiting for a decisive measurement. They are different accounts of what has to be true for the same measurements to come out the same way, and the mathematics is built such that the accounts are indistinguishable from inside. So the situation is not that we have a hard question and no answer yet. We have a hard question, several complete answers, no way to choose between them, and the growing formal result that whichever one you choose, you will have to give up something you would have called obvious. That is the reality nobody wants to talk about, not because it is forbidden, because there is nothing to do with it. And I want to be precise about that phrase, because it is the actual mechanism of the silence. Physics is a discipline organized around a specific kind of progress. You have a question, you design an apparatus, you get a number, the number decides. That loop is the engine. It is what makes physics different from arguing, and this question does not enter the loop. There is no apparatus. There is no number that would decide it. You can spend a career on it, and produce at the end an argument, and an argument is not a result. So a reasonable, honest, hard-working physicist looks at it, recognizes there is no handle, and goes back to the bench where there is one. Multiply that by 1,100 people and 100 years, and you get exactly the survey we started with. Not cowardice, not conspiracy, just 100,000 individually sensible decisions to work on something tractable, accumulating into an institutional blind spot the size of the foundations of the field. And this is where I have to say something about the wall. I told you earlier that the boundary between the quantum world and yours is not a wall, it is a rate. I meant it as a clarification, and when I said it, it was reassuring. It explained why your keys are always somewhere, why your coffee cup does not interfere with itself, Why the world at your scale behaves. It sounded like an answer. It is not a wall, it is a rate, which means there is nothing protecting you. There is no barrier, no shielding, no principle of physics that holds the strangeness down at the atomic scale and keeps it there. There is only the speed at which the room writes down what you did, and the room is a fast writer, so you never notice. But the mechanism is not a wall, it is a bookkeeper, and bookkeepers can, with sufficiently good engineering, be slowed down. That is precisely what those laboratories in Vienna and Boulder have spent 30 years doing, and every time they slow it down, the strangeness is still there waiting, at 2,000 atoms, at 1 trillion atoms, at whatever number comes next. So why does nobody talk about this? I want to answer that carefully, because there is a lazy version, and the lazy version is wrong. The lazy version says there is a cover-up, that physicists know and are keeping quiet because the public would panic, or because careers depend on it, or because the truth is too destabilizing. There is no cover-up. That Nature survey was published openly in the most prominent journal in science, with the numbers printed. The theorems are all in peer-reviewed journals with public preprints anyone can read for free. Nothing has been suppressed. What is real is a habit, and the habit has a history. For most of the 20th century, working on the foundations of quantum mechanics was a good way to end a career. It was not physics, it was philosophy, and philosophy was what you did after you stopped being able to calculate. John Bell, the man who produced the single most important theorem in this entire story, the one that turned a 30-year argument into an experiment, did that work essentially on the side, on unpaid leave from his day job at a particle accelerator, because it was not the kind of thing you were supposed to be spending institutional time on. Meanwhile, generations of graduate students were told, in one form of words or another, to shut up and calculate. I told you that phrase at the start, and I told it lightly, because it is a good joke and it is meant to be. David Mermin coined it, and he was being wry about a real professional attitude. I do not want to say it lightly now. Because 80 years of that instruction, given to bright young people at the exact moment they are most inclined to ask, is not a joke. It is a filter. And the 2025 survey is what a filter like that produces, measured in numbers for the first time, 1,100 physicists, all using the same equations every day with total success, holding flatly incompatible pictures of what those equations are describing. And, this is the part that stays with me, largely never having asked each other, not one great silence imposed from above, 1,100 small ones, each perfectly reasonable, each the result of a working scientist deciding that today there is an experiment to run, and the question can wait. And the question has been waiting for 100 years. And notice something about the collapse models, because they are the exception that proves the rule. That program did enter the loop. It made a prediction, an apparatus was built, a number came back, and the number decided. It is the only part of this entire subject that has behaved the way physics is supposed to behave, and its reward for behaving properly was to be shot under a mountain in Italy. There is a lesson in that which nobody wants to state plainly. In this particular corner of science, the ideas that follow the rules die, and the ideas that refuse to make predictions live forever. So let me tell you what I think this actually costs you, because I do not think it is what people assume. It does not make the world less real. Your keys are in one place. The sun will come up. The transistors in the device you are listening to this on will keep switching, billions of times a second, exactly as the theory says. Nothing in this video changes a single thing about your life tomorrow, and anyone who tells you it does is trying to sell you something. What it does is put a bill on the word real. You have been using that word your whole life as though it were free, as though it were the flaw. And what a century of very careful people have discovered is that it is not a flaw, it is a purchase, and there are several available, and each one costs something different. One world, or locality, or definite things in definite places, or the reliability of experiment, or the idea that when something happens, it happened for everybody. You may have any of those, you may not have all of them. That is the offer, and it is not negotiable, and it has been on the table since Heisenberg came down off that rock in the North Sea 100 years ago, with a headache and a set of equations he could not entirely believe. I find I do not experience that as frightening in the end. I experience it as a kind of enormous unexpected courtesy. Because the universe did not have to be comprehensible at all. It did not have to have rules that a species of primate could write down on a blackboard and use to predict the magnetic behavior of an electron to 12 decimal places. It gave us that. It gave us a description so precise that we built the entire modern world out of it without ever settling what it means. What it did not give us was a guarantee that the description would feel like anything, that it would come with a picture attached, that when we finally got to the bottom, there would be something down there recognizable enough to point at and say, there, that is what is actually happening. There may be. Somebody may work it out. It may be somebody who is 9 years old right now and has not heard of any of this. But if the last 100 years are anything to go by, the answer will not arrive as a discovery. It will arrive as a bill, a list of the things you have to stop believing in order to hold it. And the people who finally read it out loud will probably be the ones who never learned to stop asking. The box has not decided yet. Somewhere tonight, in a cold room, a machine is holding something in 2 places at once, and it will keep holding it for a few more milliseconds than last year's machine could, because someone made the vacuum a little better, and the whole question of what that means, the question underneath every measurement anyone has ever made, is still sitting there, patient, unanswered, waiting for somebody to open the lid.